So did you solve these questions, Nana? Yesterday's questions? So this one, did you write the products? Where the bromine is coming? Yes. So first, here is the product. This is the product we will get. So mechanism, Nana? CH3, CH, CH3, CH double bond CH2 plus HBr. So HBr undergoes H plus plus Br minus. So first H plus is coming and attacking obviously in the first position. Why the first position? Because we'll get the secondary carbocation. CH3, C, CH3, H, CH plus CH3. So then carbocation rearrangement takes place. Why carbocation rearrangement takes place? Because the adjacent carbon is tertiary carbon. So then afterwards Br minus CH3, CH3 Br, CH2 CH3. Okay, important one. Write it down. Same compound. Try this one with water. Write the product with mechanism. Write the product with mechanism. The mechanism is, so generally we will take like this. Actually H3O plus we will take. H2O plus H plus. H plus is acts as electrophile and H2O is nucleophile. This is electrophile. H2O is nucleophile. So according to electrophilic addition reaction, obviously what exactly happens? Electrophile is coming and attacking the H plus. H plus will attack the first position. So because we'll get the secondary carbocation. If it is attacks second carbon, we'll get the primary carbocation. So that is the reason. So directly I am writing that. CH3, CH3, CH positive charge, CH3. CH2 plus H, CH3 is coming. So once again same here, Nana. Tertiary carbon is here. So the hydrogen, this hydrogen hydride shift takes place because we'll get stable 3-degree carbocation. Stable 3-degree carbocation. I told you carbocation is having natural tendency of rearrangement. Natural tendency of rearrangement means what? So if it is secondary, if the adjacent carbon is having the tertiary carbon, by default hydride shift or methyl shift or whatever the group shift is taking place, it gets the stabilized carbocation. So not only we need to cross check the carbocation stability, not in terms of primary, secondary, tertiary, even we can see the hyperconjugation as well as resonance also. So generally resonance carbocation is more stabilized than the hyperconjugation than inductive effect. Okay. So then the water is coming and attacking over here, H2O, oxygen is coming and attacking over here. Right, Nana. So CH3, CH3, so O, H, H positive charge, CH2, CH3. Now what exactly happens? This oxygen takes this hydrogen electrons, H plus is going out, So particularly we will get CH3, CH3, same as it is, HBr like that only. Simply bit of mechanism, this just proton elimination is different, otherwise remaining everything is same. Directly we can write H plus plus OH minus, but according to mechanism this is the correct process, we need to follow this one. But whenever we are writing the products directly, in the place of Br we can directly add OH. Clear? So write it down. Come on, write this. Write the mechanism. Write the mechanism. So let me write the mechanism. I'll give the options here. So let me know the option. Come on, I gave the 4 options. అయితే ఒక పని చేద్దాం, ఇట్లా చేద్దాం. Let me know the options. D. D is the right answer, right? In this case, what exactly happens? CH3, 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 CH double bond CH2. So when we are using the HBr, right? So H plus plus Br minus, directly I am writing the H plus is attacking the first position. CH3, 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 CH, positive charge, CH2, H plus, right? The first step. The second step, Nana, methyl shift is taking place. Methyl shift is taking place. Why methyl shift? Because this is secondary carbocation, so we'll get 3-degree carbocation. Then the Br minus is attacking this particular position. We'll get CH3, CH3, Br, CH, CH3, CH3. So answer D will be the answer. Anybody having any doubts, please let me know. Same example, add water in presence of H plus. Come on, do it. Add water in place of Br, we will get OH. So as a homework, that one. Done? Shall I move? So I am not explaining that water one. Next, I am just trying to explain this one. So in this case, what exactly happens? If you are confusing, you can go with the carbon chains like this. Both are same, Nana. Okay. So the first H plus is coming and attacking this position because the bond is migrating to here because H plus doesn't have any electrons. So particularly we'll get the simply what we need to cross check. We need to stability of carbocation cross check. Right? We'll get the carbocation. Which carbocation it is? 3 degree. If it is attacks up, what exactly happens? Hello. If it is attacks over here, no, we'll get. Here is the carbocation. This is 3 degree carbocation. This is 2 degree carbocation. Let me know which carbocation is more stable. 3 degree. So Br minus is attacking over here. More major product. Here minor product. You may ask one question. In case of generally stability is inversely proportional to reactivity, but it's not applicable to intermediates. If the intermediate is more stable, more amount of Br minus can attack. Imagine, for example, మనకి ఒక 100 Br మైనస్లు ఉన్నాయి అనుకుందాం. ఎన్ని ఉన్నాయి? 100 Br మైనస్. సో ఇది ఈచ్ మినిట్కి ఒక Br మైనస్ అటాక్ అవుతుంది. ఇది 100 మినిట్స్ స్టేబిలైజ్ అయింది అనుకో 100 ఫామ్ అవుతాయి. ఫర్ ఎగ్జాంపుల్ ఇది ఒక 90 మినిట్స్ ఉంటుంది అనుకున్నాం స్టేబిలైజ్డ్. ఇది ఒక 10 మినిట్సే ఉంటుంది. అంటే ఏంటి ఇక్కడ 90 Br వస్తాయి, ఇక్కడ 10 Br వస్తుంది. అంటే మేజర్ ప్రోడక్ట్ వస్తుంది. 90 అవి ఫామ్ అవుతాయి, 10 ఇవి ఫామ్ అవుతాయి. అందుకోసం అది మేజర్, ఇది మైనర్. అంటే స్టెబిలిటీ డిపెండ్స్ అపాన్ రైట్ రియాక్టివిటీ. ఇంటర్మీడియట్ స్టెబిలిటీ విల్ బి ఇంపార్టెంట్ ఫర్ అస్. సేమ్ వాటర్ కూడా Br ప్లస్లో వాటర్ వచ్చేస్తుంది మేజర్ ప్రోడక్ట్. దిస్ ఈస్ మైనర్ ప్రోడక్ట్. Next, this is highly important. Ring expansion takes place in this case. I'll give the options. Try to write this. Come on, let me know the answer. C, right? C will be the right answer. The mechanism is like this, okay? So before, so rings, cyclopropane is there, cyclobutane, cyclopentane, cyclohexane. Okay? Cyclopropane, cyclobutane, cyclopentane, cyclohexane. Which is more stable? By default, cyclohexane is. If the cycloheptane is there, but cyclohexane is only the stable. Cyclohexane is existing in the different forms. Cyclic, chair form, boat form, twist boat, like that. So chair form is of course more stable. That's the reason. Whenever the 5-membered ring outside, for example, here is the outside carbocation is there. That cases, what exactly happens? Ring expansion takes place. If the carbocation is present at here. In this case, ring expansion takes place. In this case, no ring expansion. No ring expansion. So outside the carbon. For example, here is the carbocation here. In this case, ring expansion takes place? No. Whenever the outside carbocation, outside carbon, if it is having the carbocation means what? Here is vacancy in the p orbital. Vacancy in the p orbital. When the vacancy in the p orbital, so it can bond can break and it goes attacking. So ring expansion is possible here. But if the carbocation present in the ring, so ring expansion is not possible. Then first you should know this point. Next, of course, by default H plus coming and attacking over here, we'll get the compound like this. Here is the carbocation. I told you in this case ring expansion takes place. For the ring expansion, a lot of people are confusing, so it's easy. What we need to do, just it's a number game. It's a number game. Number game means what? So give the numbering like this: 1, 2, 3, 4, 5, 6. So 5-membered ring is becomes 6-membered ring, right? So particularly, I'm just 2 and 6. For example, the bond is breaking now. Electrolytic cleavage. 6 will get the negative charge. The 6 negative charge going to attack it the first carbon. First carbon. So directly we will get 6-membered ring. 1, 2, 3, 4, 5, 6. Write as your wish, no issues. Then the first carbon, what is there? Methyl group. Second position, carbocation. So remaining everything is same. It's a number game. So then at second position, 2-degree carbocation, rearrangement takes place once again. We will get carbocation here because 3 degree. So then Br minus is coming and attacking. So we will get the compound is like this. If you have any doubts, please let me know, I'll explain. So if you are missing, it's streaming in the YouTube, go back and pause the video, you can write it about that. Because sometimes, because to avoid the wasting of time, if you didn't write, so we have second option. Write this one. So I'm giving the options. Of course, directly writing the answer. 4-membered ring will becomes 5-membered ring now. If you want, you can write the mechanism. Same as it is. Do as a homework. Next, free radical addition reactions. Not for free radical addition reactions. In free radical addition reactions, no. So HBr will do one thing. So without peroxide and with peroxide. HBr without peroxide, it's an electrophilic addition reaction. So we know that it is the major product will be 2-bromo propane is the major product, and CH3, CH2, CH2Br, 1-bromo propane is minor now. Minor. HBr, friends of peroxide, So same products, but this is minor. Minor, this is major now. Opposite. So this is which reaction? Free radical addition reaction. We should know the difference when electrophilic addition reactions. 2-bromopropane. 2-bromopropane. Propane is major product, whereas in free radical addition reaction 1-bromopropane is major product now. One bromopropane is major product. Free radical addition reactions, right? Don't confuse. Free radical addition reaction. The above one is electrophilic addition reaction. The mechanism of free radical addition reaction. Right now, the peroxide we will take is benzyl peroxide here. Benzyl peroxide. This benzyl peroxide undergoes homolytic cleavage. Homolytic cleavage. Homolytic cleavage means what? What we will get? C double bond O radical 2 moles same is coming around. First step. In the second step, C double bond O radical, here is homolytic cleavage takes place once again between carbon and here, homolytic cleavage. So this becomes CO2, we'll get the phenyl radical plus CO2. C double bond O, this radical is coming on radical, so forming a carbon dioxide. Next one, so last step, HBr undergoes homolytic cleavage. So we'll get the benzene over here plus Br radical. So Br radical is important for us. Br radical has two options over here. So, but it is attacks over here because in this case, carbon free radicals. Carbon free radical, so also 3 degrees greater than 2 degree then 1 degree now. So particularly if it is attacks the first position, what happens? CH3, CH radical, CH2, Br. We'll get like that 2 degree carbon free radical. So then once again we are adding the HBr. H is coming and attacking over there, CH3, CH2, CH2Br as a major product. So Br radical is going as a byproduct. So that going to attack once again, the process is taking place. So here this is a major product. What is the main difference between electrophilic addition and free radical addition? Why the products are different means there CH3, CH double bond CH2, there we are adding the H plus, no? H plus is attacking over here, but here is Br radical is attacking. That is the main difference. So after H plus is attacking, so Br minus is attacking. So that is free radical addition mechanism. Just write it down. And one more important thing, in case of carbocation, natural tendency of rearrangement takes place, but whereas in this case, no rearrangements and no ring expansion, right? That is an important statement. No rearrangement, no ring expansion. No rearrangements and no ring expansion. Because it's highly endothermic reaction, so that's the reason. Come on, write it down. So now, do this as a homework. Peroxide. Peroxide, all are peroxides, as I do as a homework. And somewhat important in electrophilic addition reactions, no? Right, so this is one of the important reaction. Give the products. This is option A. Option B. Option C. Option D. Come on, let me know the answer. Answer C is correct. Because the carbocation first, right? So I'm just removing this compound because on it. The first carbocation is forming over here, then afterwards hydride shift is coming over once again. So this carbocation is more stable because this carbocation is stabilized by resonance stabilization takes. Okay, that's the reason. So option C is correct. This electrophilic addition reaction same takes place in alkynes, but I'll explain in the alkyne chapter, of course. And next, moving to this one, ozonolysis. Ozonolysis. CH2 double bond CH2 O3 ozone. What exactly happened? CH2 unstable ozonide is forming now. This is unstable ozonide. Whenever we are putting in the brackets in organic chemistry, that is unstable. Okay. Hello. Now, actually we can break the bond like this when we are using zinc in presence of water. Right? ZNO is going out. We will get CH2 double bond O. 2 moles, nothing but 2 moles of formaldehyde is getting them. 2 moles of formaldehyde. Right? Otherwise, simply we can use the shortcut for ozonolysis. Directly break the bond and add 2 oxygens both sides. Simple. O3 zinc in presence of water, reductive ozonolysis, CH2 double bond O, CH2. Nothing but HC double bond O H. And ozonolysis of alkenes will get aldehydes or ketones, depends on the reactant. Write it down. Now, try to solve these questions. Okay. Like that, any n number of compounds we can write it down. Right, first step lo em avutundi CH3 CH double bond O, CH2. Nothing but what? This is acetaldehyde, this is formaldehyde. CH3, C double bond O, H, HC double bond O, H. In this case, no, add oxygens both sides. CH3, CH double bond O, CH, CH3. Acetaldehyde వస్తుంది 2 moles. This is right. CH3, C double bond O, 2 moles of acetaldehyde వస్తుంది. This one. So CH3 ketone, acetone plus formaldehyde. Acetone plus formaldehyde, third one. Fourth one, 2 moles of acetone. CH3, 2 moles of acetone. Any doubts? You can ask me. Zero. So directly double bond O, double bond O. Okay. So ఈ బాండ్ బ్రేక్ అవ్వదు, ఇక్కడ కూడా అంతే. So now the bond is if the breaking like this. అంతే. So benzene cake లాగా, a cake work like this. 3 moles is coming around. Nothing but 3 moles of glycol. 3 moles of glycol. Let me know any doubt. Simple, ఏం లేదు. So where the double bond is there, just break it down. Both sides add the 2 oxygens. In this case, simply double bond O, double bond O, that's enough. And this type of questions, reverse, add simply. So this type of questions I'll explain in the next page. For example, the question is like this. Simply what we need to do? For example, this one I am just writing like this. That compound as it is. Double bond O. Right, remove water, simply we'll get the compound is like, if you can break it, we'll get the same product. For example, the compound is like this. If they are given the ozonolysis, if you are cutting like this, CO2, like that, simple. If you are confusing, you can go with the carbons, number of carbon atoms, it's easy. Okay. And reaction with KMnO4, reaction with cold alkaline KMnO4, so I'll explain that. Reaction with KMnO4, friends of H plus now. Part KMnO4 also we can see. This is application of ozonolysis, means like that. For example, CH2 double bond CH2, so KMnO4, friends of H plus. We will get different types of products over here, but I'll let you know how we need to solve this question. Here is CH3, C double bond OH, carboxylic acid and CO2. CH3, CH double bond CH, CH3, so 2 moles of carboxylic acid. So first write it down. I'll explain how we need to solve this question in easy mode. So first step, first step what we need to do, same like O's analysis. For example, the CH2 CH example, same like O's analysis, do it. So easy, right? First step. Second step, what we need to do, the double bond carbon, if it is having the H, we need to replace the H with OH. Here is 2 hydrogens are there, 2 OH groups. Here is also 2 OH groups. Remove the water molecule. Why we need to remove the water molecule? Because if the carbon is having 1 OH group, that is more stable. If it is having the 2 OH groups that are unstable, water is going out, 2 moles of CO2, 2 moles of CO2 we will get. So this exactly happens in here. 2 moles of CO2 we will get here. Okay. So first step, what we have to do? Do the O's analysis, and the double bond carbon, if it is having the H, that hydrogens are replacing with OH group. Third step, if carbon is having 1 OH group, no issues, Nana. If sometimes no hydrogens means no need to do anything. For example, CH3, CH double bond CH, CH3. In this case, first what we need to do as a O's analysis, CH3, CH double bond O, CH, CH3. This is the first step, like O's analysis we need to do with KMnO4. Next, this double bond carbon is having 1 OH, right? CH3, COH double bond O. Here also C double bond O, C hydrogen with OH, CH3, but not the adjacent, this carbons, double bond hydrogens only. Double bond hydrogens only we need to replace with OH. So 2 moles of what we will get? Acetic acid we will get. 2 moles of acetic acid. Clear, everyone? For example, like this compound is given, CH3, CH3 double bond CH, CH3. Same, KMnO4, brains of H plus acidic medium. What exactly happens now? CH3, CH3 double bond O, CH, CH3. But this double bond carbon doesn't have any hydrogens, so no need to do anything. So it's acetone only, we will get the product. But this is converting into OH group because double bond carbon is having 1 acetic acid. For example, if the ring structures are given like this, so if you're confusing, here is hydrogen is there because carbon is having the 4 bonds, right? Simply do as a O's analysis, double bond O, and I'm writing the OH. Why? Because nothing but we can write COOH, COOH. KMnO4. Here is, because already methyl is there, we can't do anything. So in this case, bottom one is converting into carboxylic acid because here is the hydrogen is there, right? In this case, directly we can write like this. Easy.